Okay, so today we change topic, and we will start developing these tools that will allow us to show the theorem about correlation functions, which is one of the fundamental properties of condensed matter systems. And the understanding of this theorem will also pave the way to understanding how there can be completely different types of order. The very nice thing about these tools that we will develop is that each of them by itself is a very interesting result, not only in mathematical physics, but it has profound consequences in all parts of physics. So I want to start with a question. What do you think is the most important physical difference, not mathematical difference, but physical difference between ordinary quantum mechanics and quantum field theory? Huh? Locality. Yeah, so can you explain, your colleague said locality, can you explain it, can you elaborate a little, in what way?
QFT satisfied Lorentz invariance, usual quantum mechanics don't. But even though we generalize to direct equations, there are still like the interaction is enough local. Like when we write down the Lagrangians, and not the local.
Okay, okay. So there are. So basically you're right. The very important thing is that in quantum field theory, there is Lorentz invariance, which means, among the other things, but the characteristic that right now we care about is that there is a light cone, which I want to say it's very sharp, meaning that there is no way that there can be causality between two events such that one of them lies outside the light cone of the other one. And this notion is very strict. So we have a very strict notion of causality. Then, you know, in quantum mechanics, there is a lot of speaking about non-locality and spooky action at the distance and all these things. However, things like entanglement or some Lagrangians that you can write, for instance, that contain topological interactions like the Bohm-Aronoff effect. Are you familiar with the Bohm-Aronoff effect? These things do not violate causality. Okay, so entanglement, it is not spooky action at a distance. You cannot send superluminal signals by using entanglement. However, the situation is much worse than entanglement. So in ordinary quantum mechanics, you can send signal or have causality at a distance, and not in some evanescent way, but you know, it seems you can do it big time. So I'll show you that you can send a signal arbitrarily far away in an arbitrarily short time. Okay, so I will first sketch a quick argument. Then when we prove whatever we are going to prove, you will see it. You will see where violation of causality may appear even more clearly. So imagine that I have a spin chain. that is prepared in an eigenstate of our Hamiltonian. So if I do nothing, nothing will happen because eigenstate is a steady state, okay? But now imagine that at t equals 0, I do a sudden perturbation. So I switch, so to my Hamiltonian of my spin chain, I add a term that has only support on the first spin. Okay? Any term. So this term does not have any special form. Okay? Particular does not have the special form such that my initial state is still an eigenstate of the new Hamiltonian. Okay? It's not like that. So this means that psi of t will evolve in this way. Okay? And what is the support of this guy? Well, we can try to understand it by expanding it. So we will have so notice that even if our Hamiltonian is local, so it's the sum of some operators in this way, here you see that the square of this guy contains terms that have this form, and in general, when you have, at some point in perturbation theory, you will get terms that have this form, that are very non-local. Which means that if I try to do an experiment on the last spin, or a spin that is very, very far away, let's say at a distance n, for every time, there is some order n such that this object will overlap with this spin. And the expectation value of an observable here will see the presence of V1. So no matter how distant is this, there is always a finite time such that you will see the signal V1. So I can send signals at any distance in an arbitrarily short time. I can, when I say arbitrarily short time, I can take even a smaller time than the one we found, and going a little bit further in perturbation theory. So I can always, I don't have any constraint whatsoever. So it seems that, yeah, okay, this is ordinary quantum mechanics. It's not relativistic. So, of course, we violate causality because it's like Newtonian physics. So that's why we need quantum field theory. That's the right theory. And we only use ordinary quantum mechanics when it works. So we could be happy like that. So, however, today I will show you a beautiful theorem due to Lieber-Robinson. I believe it's from 1976. This theorem went completely unnoticed because I guess at the time nobody understood it until it was rediscovered, I believe, in 2004, independently by Matthew Hastings, who used it to prove the theorem about correlation functions. So this is what he had in mind. But the theorem itself says something amazing. It says, in ordinary quantum mechanics, if the Hamiltonian is local, plus some other assumptions that I will spell out, there is an emergent light cone. So there is a light cone. This light cone is emergent because it's not an ingredient of our theory. We do not impose it from the beginning as a postulate, as a primordial fact of nature, as we do in quantum field theory. It emerges. It's contained in the fact that the Hamiltonian is local and that energies are bounded. So the fact that energies are bounded locally and that the Hamiltonian is local is something that we already have to assume. It's already a fact of nature. So we do not need to impose that there is a light cone, because a light cone is already a consequence of this. The only difference between the emergent light cone and the real light cone of special relativity is that whereas the light cone of special relativity, or of relativity in general, is sharp, this one is fuzzy. So what I mean is that instead of being a light cone like this, it's a light cone like this. Which means that you can actually kind of send a signal here, and then it gets lost. So we need a precise statement for this thing. So the statement that, so as you know, a light cone is defined by d minus vt. This is the distance between the two objects. This is the speed of light. This is time. So you know that if d is larger than vt, there can be no signal. So we want to say something slightly different. We want to say that outside the light cone, so when d is greater than vt, our signal must vanish, and vanishes more and more as we get away from the light cone. So it's not completely sharp, but we want, a very strong vanishing of this. So we want to say that whatever signal we have, it vanishes in this way. The other difference is that whereas v in quantum field theory or in relativity is assumed to be the speed of light, there is no reason why it should be the speed of light. I mean, it's a fact of nature. There is not something that we can argue that has to be the speed of light. So it's a postulate. But here, because the light cone is emergent, the value of v is emergent. Means that this is, you can derive this value from the Hamiltonian. Okay, so let's do it. Let's prove it. So our hypothesis is that first the Hamiltonian is local. So I can write it in this way, like the sum of local operators. We also require that the maximum number of points that you have inside any of these supports is upper bounded by some number that we used to call large R. So let me use sigma. And also, we want locally the energies to be bounded. So this means that we require that phi x, for every x, this norm is upper bounded by some number h. Okay? So this h is the one that binds all the interaction terms in one Hamiltonian. And we will prove our theorem using so we will see what consequences this has. In particular, it has the consequence that we cannot send signals. But what we will do is the following thing. So we imagine that we have 2 points, A and B, or there can be 2 regions, A and B. And we have operators A and operators B with support in this region. Okay? And we want to understand what happens to the commutator between A and B. Because if 2 operators commute, it means that I can measure one of them without caring about the expectation value of the other. However, if there has been a signal between A and B, that means that whatever has happened to A then must influence B. So in turn, this must imply that, that A will not commute with B. So in order to show that there is, in the end, no signaling, our strategy will be to show that if A and B are outside the light cone, then they must commute, or almost commute, in this sense. So what is that we do? So at t equals 0, A and B have disjoint support. And if you remember, because we are dealing with the bosonic systems, they must commute. So at t equals 0, nothing happens. But then we make the system evolve, right? So A becomes A of t. And for the sake of simplicity, without any loss of generality, let me just keep my old B. Okay? I can just keep B the same. There is no real loss of generality. And compute this guy. Now you see that what is A of t? A of t, by definition, is just e to the iht A e to the minus iht. So you see again from the same argument in perturbation theory that the support of this unitary operator is everywhere. Because even if h is local, when I exponentiate it, the support is everywhere. For every t. So for every t, A of t has support everywhere. So for every t, this will not commute, which is our problem, right? So what I want to say is that they almost commute, so which is not in contradiction with this. So what I want to show is that AT and B, their commutator is small. So small means that I take the norm, and now this number is small. If what? if the distance between A and B is greater than the time t times something that we call speed. I mean, it has the dimensions of a speed. And this B, we will see what it is. It depends on the Hamiltonian. Okay, so this is our strategy. So for the sake of just for notation simplicity, let me call f of t this commutator at and b. Okay, so how do we prove this? So the first thing I want to do is to take the derivative of f. Okay. So if you remember how you take derivatives in quantum mechanics, which you can immediately see if you differentiate this object, this is equivalent to commute. So you have a minus I, A of t, h, b. Because the commutator with b is a linear operator that does not depend on time. The time dependence is in A of t, and the derivative of A of t, try to do it, is minus I, the commutator with h, which is the Heisenberg equation, right? Very good. And now notice that h is also equal to h of t. In a trivial way, because h does not depend on time. So I can write if u is e to the minus I ht, and h does not depend on time, then obviously h and u commute, which means that I can always write h of t as u dagger, which is what I call h of t. So, and this is UA U dagger, right? So this means I can write minus I U A H U dagger commutator B. You agree? And now I want to use the fact that our Hamiltonian is local. So it has this form. So I plug it in, and we get minus I u, so minus I, the sum over all the x's, u a phi of x, u dagger b. So now we see something that, so what are these phi of x? So this is our A, right? This is our B. And the phi of x are all the patches on which our interactions are defined, right? Our Hamiltonian is the sum of interaction terms that involve up to sigma degrees of freedom inside each of those bubbles. But you see, this interaction term, so for this x, so I have this phi of x, this x that is far away from A will commute with A. So not the whole Hamiltonian will commute with A, but this interaction term, it will. So you see, the only way that possibly this term may not commute is if x has a non-zero intersection with A. So if I call Z1 my axis in my lattice such that, so let me call them the x1s in my lattice, such that x1 intersection A is different from the empty set, and I restrict my sum to this set, nothing changes. Because those that are not in here cannot give you contribution to this commutator. They would be automatically 0. So I can just write x1 belonging to z1 here. Do you agree? Very well. So now we use a trick. Oh, after I've done this, I can also plug back the u's and write again that this one is A of t. Right? I put them inside the commutator again. But now we use a trick. We use the Jacobi identity. So we will write you're familiar with this identity, right, for commutators? So the interesting thing about this formula now is that, as you can see, in here, we find again F, the commutator between A, T, and B. So what is that I'm doing? I have some linear operator, because I'm taking F, I'm commuting it with these Hermitian operators, and then I'm doing a sum over all these commutators. So this part, I can write it as a linear operator on F. And then this one is another linear operator that does nothing to F, that I call G. Okay? Of course, they are both depending on time. So our equation has become F prime equal LG plus F. So this is an ordinary first order linear differential equation. We know how formally to solve it. Because the way we solve it is by first taking the solution to the homogeneous equation. So the homogeneous equation is F prime equal L of F. And then we add to this solution a special solution given by the non-homogeneous term. So how do we do that? So I'm only going to solve it formally, right? Because I don't know what is the exact form of L. So, and in general, solving it may be difficult. But let me just call gamma t, the map that gives me the solution to this equation, such that at t associates gamma t f0, which is f of t. So this is the solution to the homogeneous equation. We know it exists. So I don't know what it is, but we know two things. First, that it exists. And second, notice that L is the commutator with the Hamiltonian. Because the sum over x1 of phi x1 is still an Hermitian operator. So the other thing that we know is that gamma t is a unitary operator. Since it's the solution of the differential equation that is the commutator with the Hamiltonian, this must be a unitary operator. So this is the homogeneous equation. So what is the full equation, the full solution is that f of t is equal to gamma t f of 0 plus, well, how do we do that? We have to add what happens when we integrate g. The exact way you do this is that, so you have g of s ds, and you first do like this and then like this. Yeah. Okay. So the interesting thing about this is, again, that gamma is a unitary operator. What does it mean? That if I take the norm of f of t, remember that in the end we are interested in finding something about the norm of f. This will be equal to the norm of it will be smaller by using the triangular inequality than the norm of these two pieces. But the norm of this is again f of 0. Because this is unitary, so it's norm preserving. So this is the important property of unitary operators. Remember when we talked about measures, we said that the Schatten norm is invariant under unitary transformations. So this is what we are doing here. So we have the norm of f of 0. Then plus, I can bound by dragging the norm inside here. And again, all these gammas don't count. And I can write this thing in this way. So you see, we have some bound. So this is the norm of A and B at time equals 0, which would be 0 if X does not overlap with A. But we don't know if it does, right? We are not putting any assumption in this. Plus, we integrate the norm of GS. So in order to proceed with our bound, now we want to find the bound for this guy. So again, what is GS? GS is the commutator of phi x1b with A. Okay, so we want to understand, we want to find something for this. So we know that this will be upper bounded by write everything right? Yeah. Very well. Now, you see, in some sense, this problem here is the same problem that we had before. Is to try to evaluate this commutator. So we can do the same trick. We can take the derivative of this guy. So let me call this function f1. So if I take this derivative, this will be equal to minus I, the commutator of phi x1. So remember, phi x1 is depending on t, because I pulled back the u's before, h, commutator b. And again, I can write that. So I'm looking only at this guy. Well, let me see. Yeah, let me call it this way. And this one is phi of x. And here I have the sum over all the x's. And again, I can pull out my u's. And now I see that the only way this commutator can be different from 0 is if x1 has non-null overlap with x. So before it was a to have non-null overlap with x. Now it's x1. So now I can define a set z2 that are those x1 that belong to z1, such that x1 intersection with x is different from the null. So from now on, I can label these ones that have this property. I can call them x2, okay? But they must belong to z1 first. So here I can put a 2. And again, I will be able to upper bound phi 1 using the same thing. So f1 will be upper bounded by the commutator of phi x1 b. There is already here a commutator with the a, so it will be equal to this norm, this norm. I'm using the fact that the commutator between a and b is upper bounded by 2a b always. This is what I used. So this guy is upper bounded by sx1 sum x2, 2a, the commutator between phi x1 and B. Okay? So you see that if I do this okay, yes. And this guy will be upper bounded, so we have 2a here. And then again, so we will use our Jacobi identity. So I think I missed the piece. Okay, yeah, I went too far. Okay, we're here. Yeah, yeah. So, okay, so we have this thing here. So we know that now this has this form. So this has this form here. And now we can write this thing as phi x1b. I forgot to do the Jacobi identity, plus phi x2b. Okay. Very good. So this will be the norm of F1 will be upper bounded by the sum of x2 to phi x1. This one was A. Oh man, I'm lost. Okay, let me see again. Oh yeah, because, okay, so we have a 2a here, and then the norm of phi x1 b. Okay. So we have this thing here, which is okay, and then we have this thing here, like this. Okay. All right.
Sorry.
Yeah.
I don't quite get how you go from there. I mean, after F1, the second order.
Here?
Oh, yeah.
Okay. So we know that GS is upper bounded in this way. And now we want to upper bound this part. So this is what we call F1. So we take the derivative, and this is the derivative of fx. It's the same thing that we did before. We differentiate with the phi x, because it's the Hamiltonian, and then we commute with b. But now we know that this must be x2. Must have a non-null overlap with x1. Okay, so we get this thing. Okay. So from this, we know now we can write it as, by using the Jacobi identity, as phi x1 b commutator phi x2 plus phi x2 b commutator phi x1. And this one is our F1. So when I try to do the norm of phi of x1, I know that this will be smaller than the sum over x2. The norm of this at time equals 0, so which will be equal to 2 times 2 phi x1 phi x2 b, because I have two commutators here, and plus I have to integrate between 0 and s, because this is a g of s, and now I have 2 phi x1, the norm of phi x2, commutator b. Okay, that's correct. So, and now this guy goes inside this. Okay? So what we get is that the norm of f of t is upper bounded by the norm of AB, or commutator AB, plus the integral between 0 and t. Then we have 2a and I have the sum over x1, the sum over x2, okay, first of all, I must have a term where there is no sum over x2. It's only the sum over x1, which is, yeah. Is this commutator at time equals 0? Okay, so it is 2 pi x1 b, okay, plus, so this guy is this thing, 0 and s, 2 phi x2 phi x1 this is phi x2 commutator b. Okay. So I can continue. Now I want to bind this one. So if you do it many, many times, you see, you keep conserving always the same structure. And what you get at the end is that f of t is smaller than the commutator between a and b in norm. So plus 0t 2a, and then we have sum x1 phi x1 b plus the nested integral. Now we have 2 to the 2, again a and b, and now we have the sum x over x1 and over x2 of phi x1 phi x2, and then I keep doing that. So I have 0t, 0s, 0. So let me call this S1, S2, 2 to the third, again AB, and now the sum over the patches on x1, patches on x2, patches on x3 of all these guys, fx1, phi x3, phi x2, phi x3. Okay. And so on and so forth. Now I can use the fact that every phi of x is upper bounded by h. So if I do this, this is upper bounded by h cubed, right? And this is upper bounded by h squared, and this is upper bounded by h. So you see, and this is upper bounded by h to the 0. I mean, there is this part plus a part that depends on h to the 0. So this thing that I can upper bound everything in this way, I do have. So also let me say that this guy, AB, is upper bounded by, so if A and B have no overlap, this one is 0. If they have some overlap, it's for sure upper bounded by 2AB. Okay? So I will call the number of ways in which A and B may not overlap sorry, the number of ways in which they overlap, sigma x 0. It's a number. It's a number. Okay. So here we have, putting everything together, I can write this thing in this way. I have 2AB that appears everywhere. Sorry, AB appears everywhere. Then we have 2 to the n. We are summing over n, right? N goes from 0 to infinity. I do it infinite times. At 0, we just have this time this sigma x 0. In general, we have the sum over x0 xn. And then we have h to the n. And then we have all these integrals that are integrating nothing, because nothing else depends on time anymore. But they're there. And this guy also is not summing over anything, because we have upper bounded everything. So it does not, there is nothing here that depends on x0, x1, x2, x3, and so on and so forth. So what is this? This is just the number of items that are in these sets x0, x1, x2, xn. So how are they defined? Remember, x0 is the number of ways that A can overlap with B. And x1 is the number of ways that A can overlap with something that is in the Hamiltonian and then can overlap with B. And so on and so forth. X2 is the number of ways that A can overlap with phi x1, that can overlap with phi x2, and then can overlap with B. Okay? So this number is the number of paths between A and B. It's a graph theoretic number. You see, it's just a number. It's a number of paths. Because the Hamiltonian is local, if there is no path of interactions between A and B, then they cannot interact. But you see, we have many, we're summing over all of them. Okay. So we have, so let me put things together here. We have, let me just rewrite it. We have 2 to the n, h to the n. Then we have this stuff. So you remember the Dyson series. When you integrate the Schrödinger equation, you have exactly this, right? You first integrate at a shorter time, then you integrate at a larger time, and so on and so forth. And this is, in fact, what we are doing. And you know that this integral can be written like 1 over n factorial, all integrals between 0 and t, n of them. This is an identity. So, but now they are integrating nothing, right? So they're integrating the identity. So this is upper bounded by t to the n. So here we have t to the n over n factorial. And then we have our number that is a graph theoretic number. So as you can see here, there is an exponential that wants to come out, right? This is the series for an exponential. So, but yeah, this number is not an exponential. So it would be nice if we can bound this number with something that is an exponential. So how do we do that? So first of all, note that for sure, the number of paths between A and B must be of length n, right? This is the number of paths of a certain length. This depends on n. So let me call it Sn from now, sigma n. This number of paths that connect A and B is for sure smaller than the number of paths of length n. This number of paths of length n that do connect A and B. But then I also have the number of paths of length n. Some of them go somewhere else, right? So this is an upper bound. And this number of paths, because a path is made of interacting pieces, cannot be bigger. So the total number of paths of length n cannot be bigger than sigma to the n. Because sigma is the maximum volume of any of these bubbles. So there are at most sigma ways that they can interact. And in a path of length n, there are at most sigma to the n ways that they can interact. So this is the total number of paths of length n. Now we want to use the fact that they must connect A and B. Okay? And now we use this. If the distance between A and B is greater than n times r, where r is the maximum diameter of X. Okay? So what I'm counting, so how many bubbles I have and how long is one of the bubbles. But if the distance between A and B is larger than this, then in this case, sigma n must be equal to 0. Because there is no path that connects A and B. So since it's 0, I can upper bound it with any number that is greater than 0, right? So I can upper bound it by sigma to the n times e to the nr minus d. When dAB is smaller than nr, then there are some paths that connect A and B. But for sure, they are smaller than sigma n. for sure this is smaller than sigma to the n. And now I can further upper bound with any number greater than 1, right? Look that in this case, this number is greater than 1. So I can upper bound it in this way. So you see that this guy is the same. It's an upper bound in both cases. But it takes in account the fact that you must connect the A and B. So all this is upper bounded by the series from 0 to infinity of 2 to the n, h to the n, t to the n over n factorial. And now we have all these guys that is sigma to the n, e to the n r, and e to the minus d. Let me erase this. So this guy does not depend on n at all. But now this is an exponential. So this becomes, and I forgot 2ab, right? There is 2ab. Everywhere. So this is 2a normal b exponential of 2ht sigma e to the r minus d. So let me manipulate this thing a little bit. So let me call I can just call 2h sigma e to the r. Let me call it v. You see, we are using the graph distance, so the speed has just the dimensions, so it's a pure number, so the speed has just the dimensions of an energy. So these are numbers, pure numbers, and this is an energy, so this has the dimensions of a speed. And what you get is that this is equal to 2ab e to the vt minus d. And this is the result that we were looking for. If t is large enough that vt is greater than d, then this bound means it's a very poor bound. We know that a and b will not commute, okay? Because we can reach b. So we don't use it. But when vt is smaller than d, so outside of the light cone, then the norm of f, which is the norm of at commutator b, is exponentially small in the distance between the light cone. So in spite of the fact that a of t has support everywhere, actually how much it doesn't commute with b is an exponentially small number in vt minus t. So this defines the maximum speed of signals in this Hamiltonian system. Yes, you can, and this defines the emergent light cone. So you can see v only depends on the properties of the Hamiltonian, because h is an upper bound onto the strength of the interactions, and sigma and e and r contain the properties of the graph. That is a property of the Hamiltonian. It's how the interactions are. Okay, so this is the sought-after result. which is pretty amazing, because we start with a theory that has no Lorentz invariance, no causality, but the very fact that it's local, and the local density of energy must be finite, implies that you cannot transmit signals. So tomorrow we will see why this commutator, before I sketched an argument, but tomorrow we will see exactly why you cannot, if this commutator is small, then you cannot send signals outside of the light cone. So when I first met this theorem, I thought it was really amazing that a structure like the light cone can just emerge, that you don't need to impose it from the beginning. So many people think that, maybe also the Lorentz symmetry can emerge, or gauge symmetries can emerge. Because at least this very remarkable feature can emerge. Okay, see you tomorrow.